So basically, Dijkstra shortest path algorithm is it is shortest path from single source to all vertices for a weighted graph. So we'll go step by step. I have an example also here. So let's take, this is the graph you have, right? In this graph, these are the vertices and these are the edges, correct? So single source to another path from shortest path from single source. So there has to be one source here. Let's say A is our source. So this algorithm is for if you want to calculate the shortest distance of B, C, D, E, and F from A. Basically, shortest distance of all other vertices from the source vertex. So if that is your problem, then Dijkstra algorithm is used there. And weighted graph. What does weighted graph means? That you should know what is the weight of edge connecting each node, because that's what Dijkstra uses to calculate the shortest distance. This could be the distance. This could be any other parameter. This could be the cost of fuel or anything else, right? At least some weight should be assigned to each edge. The time complexity is v square. V is the vertices, number of vertices, order of v square. I hope we all know time complexity. How much time it takes, basically. What is the order of time, basically, big notation. Now, if you use a min priority queue, and we'll discuss minimum priority queue later, then the time complexity drops to order of vertex, number of vertices plus E is number of edges log V. And we'll discuss this at some other time. What is the limitation of this algorithm is it does not work with the graph which are having negative weights. For example, here are positive weights. If you have negative weight, then it will not work. So if we get time, we'll discuss that also. Now coming back to how this whole algorithm works. So let's say you have this graph A, B, and A is connected. There's a connection between vertices, and each edge has a graph. Now what is our problem? First, let's assume our source is A. Our problem statement is we want to calculate the shortest distance of each of these vertices from A. Now, how does it go? So there are, so we'll go, the source is A node here. Now, first thing we do in this algorithm is we mark the distance of each vertex or each node from A to infinity. So everything is marked as infinity. Now we follow one rule, and this is the main crux of this algorithm. This rule is if source to destination distance, let's say we are calculating from A to C, for example. So A to C is via this path and via this path, correct? So if source to destination distance is greater than source to current distance, so let's say we are at node B. Let's consider two scenarios. We are at node B, and we'll see how to navigate from A to B. We will go over this chart soon, but let's say we are at node B. Now the distance of A and B is 5, and B and C is 4. So source to current distance, which is B, which is already 5, plus current node to destination distance. Current, we are at B, this is current node to destination C, so 4. 5 plus 4. Remember, in the beginning, we have marked everything as infinity, correct? So infinity, 5 plus 4 is 9. 9 is, 9 is less than the infinity. So that means the distance of C becomes 9 in that case. So this is the main formula, correct? So it should be less than, actually. I made a mistake. Is less than, correct? So we should mark this here also is less than. Now we'll go over example. How this whole thing works. So our source node is A. Problem is we want to find the shortest distance of each node from the A node. So what is our first iteration? Okay, let's go to the rules. Then we'll go over this. The rule is at the beginning mark all distances of all vertices from source node to as infinity. Now any node pass. So when we navigate, we start from A. We start navigating. Once we start navigating, whatever node we have already navigated or visited, we'll mark that node as visited and we won't consider that node again. Neither we will visit, neither we will consider for any other calculation, and we'll see in this graph how does that happen. This formula we already covered. And now this last point I will hold on. This will become clear once we go over this. Now let's go over this. We start from node A, right? Now the A to B, A to C, A to D, A to F, A to E, all are infinity. So we start from node A. Now A, and we mark node A as visited. So this red means it's visited. A to A distance is 0 anyway, so we won't consider it. A to B is 5. So we mark this as 5. And A to D is 9. So we mark A to D as 9. And rest everything we mark as infinity because we don't know the distance yet. Now the one of the key thing here is, now we have from A to B and A to D. Which one is minimum of whatever we have in this row? 5 is minimum, right? We won't consider A. So 5 is minimum. A is our current node, so we'll skip that. So 5 is minimum. So we'll choose 5. Now out of 5 and 9, choose 5. 5 is node B. So we have chosen node B. Now what we do is, we remember that from A to B, distance is already 5 because our purpose is to calculate the distance from A, not from B onwards. So A to B, we have chosen B here. So the distance from A to B is 5. So we put 5 here. Now we are at B. So we mark B as visited. So A is visited now, B is visited. Now, what are the nodes connecting to B? So B is connecting to E, B is connected to D, and B is also connected to C. So let's calculate the distance between B and C. So B and C is 4. So B and C is 4. And the current distance between source to B is 5. So total distance between source to C becomes 9. Now this 9 is less than infinity. So we'll keep 9. Now B to D. Now let's say B to D. So B to D is 6. So B to D is 6 and we already had 5, A to B, correct? So 5 plus 6 becomes 11. But 11 is greater than 9, right? Because A to D was 9 already, correct? A to D was 9. So we'll keep 9. So it's the minimum of 9 and the minimum of 9, which is this, and the distance via A, B, and D, which is 11. So minimum of 9 and 11 is 9. So we'll choose 9 only. Okay. So now let's go to the third one. So B is connected to E also. So distance between B and E is 8. And distance from source to B is 5. So 5 plus 8 becomes 13. Now this 13 is less than infinity. So I'll keep 13. Now B to F is no connection. So we'll keep it as infinity. Now we have 9 and we have 9 and we have 13. So what is the minimum of this? We can choose any one of this. There are 2 9s, right? So we are choosing C. So C is our minimum out of this, correct? We could have chosen D also. It would have meant same. So let's say we chose C. Now the distance between source to C is 9. We keep that here, right? Minimum distance between source to C is 9. So if you see 5 plus 4 is 9. There are other distances from source to C. 5 plus 6 plus 11 plus 14. But we do when we going through this flow, you will find the minimum distance automatically. So between A to C is 9. So because you have chosen C as the current node now, and source to C is 9, so we'll keep 9 here. Now we are at C. Now, which are not connected to C? C is connected to B, but B is already marked at visited, so we won't even consider it. C is other than B, C is connected to node F and D, correct? So let's say what is the distance between C and D? C and D is 3. So we already have a source to C is 9. So 9 plus 3 becomes 12, C and D, correct? So 9 plus 3 becomes 12. Now this 12 is we already have between, so we are at node D. The A to D distance was 9 already. Now when we go from C to D becomes 12. So what is the minimum between 9 to 12 is 9. So I'll keep 9 as is because we know the distance from A to D, from source to D, 9. So we keep 9 as is. There is no connection between between C and E. So I'll keep that same as 13. Now there is a connection between C and F. So C and F, 8 is there, correct? We already have distance from the source to C, which is 9. So 9, sorry, C and F, I'm sorry, C and F is this. So it's 10. So we already have 9. So 9 plus 10 becomes 19. So now we have, what's the minimum between this 9 and 19? So it's 9. So we chose D is our next node. So now D is our next node. So we know the distance between source to D is 9. Source is our A. Minimum distance between source to D is 9. So we'll keep 9 here. And we mark now D also as visited. So A, B, C, D are all visited now. Correct? Now D is connected to E and F. It is connected to B and C and A also, but B, C, and A are all visited. So we won't consider those. So D is connected to E and F. So between D and E is 7. So between D and E is 7. So we already had 9. So we add this 7 to the existing 9. So it becomes 16. So now 16 is greater than we already have between source to E 13. So we'll not consider the 16. We'll keep 13 as is. Correct? Because the shortest path to go to E is this 8 plus 5 13. Not this. Correct? Because this is greater. So we'll keep 13 as is. Now between D and F. So D and F is 8. So we already have 9. So 8 plus 9 becomes 17. Correct? So we already had 19. Now we have 17. So which one will choose? Which is minimum? Which is 17. So we have chosen 17. So we have in this row 13 and 17. Which one is minimum now? Minimum is out of these two is 13, which belongs to node E. So now we mark node E as visited node and mark node E as our current node also. So now node E is connected to F. It is connected to B, D also, but these are visited nodes. So we won't consider it is connected to F. So now between node E and F is 11. So we already have 13 from source to E, which is distance between source to minimum distance between source to is 13. And we add 11 here. So 13 plus 11 becomes 24. But we for node F. So this is 24 if you go via node E. But we already have source to F as distance 17. So what is minimum between 24 and 17? Which is 17. So we chose 17 here, right? So this 17 is chosen. Now you see the distance between between A to A is 0, between A to B is 5, between A to C is 9, between A to D is 9 because 9 is chosen, between A to E is 13 because 13 is chosen, and between A to F is 17 because 17 is chosen. Correct? There is you cannot find any other path which has distance from A to any other node, and that distance is less than any of these. In short, this is our Dijkstra algorithm.